All right. Yes, he started. Okay. All right. So, all good. What happened? It doesn't go to slideshow. Yeah. Okay. Good afternoon. So today is a key lecture. Okay. So we have crossed the halfway mark. So this is the make or break lecture for this course. So we're going to talk about two key techniques, namely gradient descent and logistic regression, both of which open the gateway to regression, machine learning, and so on. All right. Okay. Let's first look at gradient descent. So suppose we have a data set which consists of a large number of independent variables. So you want to correlate the output variable, for example, rainfall or whatever, rate of mass loss of a glacier or aerosol optical depth or what have you stuff, wave height or what have you stuff. So there are a series of independent variables, x1 to xn. Y is your dependent variable, so you want to fit. Okay, so we would like to fit a model. However, a direct solution, as was presented earlier, the linear least squares, requires the solving of a large number of equations because there are many variables involved, and it's not possible to do a direct solution, or it is in some complicated form, right? So you're not able to. It is in a nonlinear form. For example, you cannot simply do the least squares and just say that finally it reduces to a set of simultaneous equations, which I can get A equal to B equal to C equal to. That's all okay for teaching. It's all good for learning. It's good for setting up question papers and giving marks and grades. But real life, if it is nonlinear, how do we solve that? Okay. Even in the case of problems in which a direct solution is available, it is computationally inefficient to do so. Therefore, we'll have to go to what is called a numerical technique. Okay. So the question before us is, are there any alternative methods? Of course, yes, there are. Okay. Now, the gradient descent is a powerful technique. It's an alternative way for minimizing a cost function rather than always looking at the Newtonian approach of if y or j is the function, then dou j by dou a equal to 0, dou j by dou b equal to 0, dou j by dou c equal to 0. Three equations in three unknowns. For example, if you want to fit a plus b1, a plus b x1 plus c x2, it's linear in two variables. We can also make it linear in two variables if it is of a power law form. For example, if it is like this also, you can do that, right? As we already see that. If it is like this, then your ln y equal to ln a plus b ln x1 plus c ln x2. It's nothing but y equal to a plus b x1 plus c x2. So don't think that it is very elementary. Y equal to a plus b x1. It is just linear. Linear in two variables could also, the original form could be a power law. And power law is all the time used in fluid mechanics, heat transfer mechanics. Many problems can be solved. It's a very powerful approach, okay, of correlating independent variables against a dependent variable. So what is the funda behind this? We build a cost function with a large number of variables, and the objective is, okay, and the goal is to see if the cost function is coming down, okay. So we iterate through various parameters, which means it's an iterative method. So it's not a one-shot method like linear least squares where we said a equal to sigma xi whole square minus n sigma xi by sigma xi by blah, 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 whatever. And b equal to n sigma xi. You can't get a single shot, okay? A single shot answer is not possible. So therefore, you'll have to start with a set of parameters, and then there'll be some cost. And then how do we move around? How do we navigate through these parameters such that the cost function or your error, least square error, what have you, the way you call it, loss function or whatever, keeps decreasing, okay? So we iterate through various parameters, moving the direction of maximum change. The maximum change goes in the orthogonal direction. That is the result which we have from vector calculus. And then evaluate the cost function. So whenever we achieve the lowest cost function, whatever it is, or a cost function which we say is low enough to be acceptable. So when the j or y or the s, sum of the least squares becomes less than 1e the minus 6, 1e the minus 4, 1e the minus 8, depending on your criterion for stopping. This is called the stopping criterion. We concluded the parameters at that state give the best fit for the model.
This is the essence of a technique called the gradient descent. Okay, this is the, so basically this is the funda behind this. Okay, consider a model. Consider that a model is built using training examples. So in machine learning, the parlance of machine learning, we don't call it as a dependent variable, independent variables. We call it as a hypothesis function. It's called H. Okay, the hypothesis function H. Because it is an hypothesis, because you have a lot of data, you're hypothesizing, because you didn't go to the governing equation, you didn't do a control volume, you didn't do a FBD, free body diagram, what is the force acting across left to right to whatever, then F equal to MA, Fx equal to MAX, Fy equal to MAY, Fz equal to MAZ. Thanks to our Newton, you do all that and force balance, blah, 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 and write a differential equation, put an initial condition, solve it, whatever. You don't have any of this. You've got a lot of data. You have a lot of data about rainfall last 200 years. You've got a lot of data about the tracks of cyclones in the past. Okay, you have a lot of rainfall about drought. So you've got data from all the rain gauges of all the IMD as the data set you acquired. Now there is no function like, so we always look at the analytic way of looking at things, right? So there'll be so you go through various courses, there'll be statics, there'll be dynamics, blah, 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 theory of machines and all that, right? And then you put a control volume, governing equation. It is not there now. But there's a lot of data, but we know there is a dependence. Okay, so we know what is the cause, what is the effect. So the idea is to be able to understand, okay, and quantify such that if you give the various causes, you will be able to get the effect with a view to predict in the future, which will help the policymakers do some decisions, or you can take some critical decisions and so on. Therefore, it is called a hypothesis function in machine learning, H of X. Let's say we got a linear hypothesis function. H of X is W1, X1, all the way up to Wn, Xn. Okay, this could just be Hx is the probability of you crossing a road. Okay, when the traffic, you crossing a important junction, say MG road, you want to cross. So no, sir, I won't cross. There is a subway. So let's forget about those arguments. You want to cross a junction where there is or MS Ramaya. Okay, backside. So there is, so X1 could be, X1 variable could be that it is showing green for the pedestrian. But this is India. You cannot just cross because it is green. Some auto rickshaw will come and hit you. Therefore, X2 is finally finding out whether auto rickshaw is coming on the left side or right side. Then X3 is whether BMTC bus is coming or not. X4 could be your present state. Whether you're carrying an Amazon package, you're carrying 5 kg atta, for 10 kg rice in both your hands or whatever. X5 could be somebody else is with you, your old uncle or grandmother or somebody is there with you. So in all these cases, there is a W1 equal to Wx to all that. Now, if you put all this into a model and get the values of W1, X1, Wx2, then if you give X1, X2, X3, the neural network will finally tell you, this hypothesis will tell you 1. If it gives an answer of 1, you will cross the road. If it's 0, you won't cross the road. So this is essentially that. Where is the model? Where is the free body diagram? Where is the law? Where is the conservation of momentum? All that is not there. But this event happens every day. Every day we cross the road. Like that. So the idea of computer science, what they are doing is they're trying to give numbers to everything. They give numbers to your behavior so that they can hypothesize and then get a rule and see whether this rule works or not. If the rule is broken, that is also added as a data. So this is the essence. This is the essence of this hypothesis function. Let's proceed further. So this is a linear combination of all these variables. Okay. Now you just sum it as very nicely the Greek symbol sigma, j equal to 1 to n wj xj. In the previous example, the hypothesis function was a linear estimator. What is a linear estimator? You tell me the height of the student, or you tell me the age of the student, I'll give you the height. Is that correct, class? Is that correct? Was it the first function we did? Can somebody respond? I'm not able to see you because I'm looking at the PPT. Is that correct? Oh, somebody should respond. Hello? Hey, Girish, am I audible?
Yes, sir, you are audible, sir.
Yeah, so that was the first example, right? One regression, which the Python code, by the way, the Python code has been shared by Pratik. For whatever it is, I forgot what the Python code is for. It's one of the earlier problems. All right, let's proceed further. Now we define the mean squared error as the cost function or the loss function. Okay, you can say that. They call it, computer science people call it as the loss function. Okay, we call it as a cost function J. Okay, over M training examples. There are M training examples. There are M situations. Okay, there are M situations of individuals crossing the road. Okay, so somebody is observing. Some student is saying morning to evening is observing. He's taking a note with paper and pencil. He is sitting at the signal from morning to evening, Friday, Saturday, Sunday. He has got some 200 examples. So M equal to 200. That N is basically the number of attributes or features or variables. So please note that there is a difference between N and M. N is the number of variables in the hypothesis function. M is the total number of samples. Okay. J equal to 1 by 2M. But that 1 by 2M is basically for convenience. It could have been 1 by M. What is that 1 by M? It's the average square of the error. Okay, across the samples. 1 by 2 is basically, I'm going to differentiate it, so I'll get a 2 of something. You know that so if you differentiate something to the power of 2, you'll get 2 of that, so 2 will get cancelled. There is some slight cheating, okay, some jugaad there. Anyway, that's okay. So h of xi is the proposal minus y of I whole square. Yi is the data. Now, as said before, we need to move in the direction of the slope. Okay. Direction of the slope, this is obstructing of the cost function with respect to the parameters. This result comes from vector calculus. You know that, right? So if you want to go to the shortest distance from here, at this point, you'll go in a direction orthogonal to it. Okay. So this is the surface. So this is called the orthogonal direction. So more than 2, we cannot visualize. So we have to use that. You from vector calculus, you take a partial derivative, and right. So you will so x1 of x1, x2, x2 of I plus j plus k plus whatever. Okay, where I, j, k are the unit vectors. Okay. So in a sense, we need to take the partial derivatives of the j, the loss function with respect to w. So once you put dou by dou of wj, the particular weight of jw, is basically take this function. So if you do this, so what you will do is you will take 2 of h of xi minus yi. That is the first, okay? 2. So it is all right. So the 2 goes. Come to the next one. 2 goes. 2 of hxi minus yi. What is the jugaad there? Because the minus hi, the minus and minus, we want to adjust by putting it to h of xi minus yi. Then the dou by dou wj goes on. Yi minus wj xji. Please note now that yi is a data point. It cannot be differentiated. So go further. Xj is also a data point. So what we are looking is a derivative with respect to the wj. Therefore, dou by dou wj, what is given in the bracket, that I'm talking about the last term on the right hand side of this equation. So that will simply turn out to be xj of I. Now, so cutting a long story short, what we started out as the blue, which looked like a menacing expression, reduced to 1 by m sigma of the loss function into xj of I. Okay, into xj of I. Now it is summed over all the it is summed over all the samples. Okay, so this will give you the partial of the loss function with respect to the partial of the weight for that particular j. Okay, for that particular j. Like that, there are as many j's. There are as many j's as there are attributes or features or variables. Now, is everybody with me up to this? Is it okay? Can we proceed? Can somebody respond, please?
Sir, I couldn't understand in the second step, how did we get dou by dou wj yi minus wj xj to the power I?
Yeah, because h of xi is that, na? We are taking with respect to only wj.
Oh, okay. Thank you, sir.
All right. Okay.
Yes.
So let us now proceed further. Okay. So finally, the learning rule will be wj of new will be wj of previous plus alpha. I will work out a problem in the blackboard. It will become clear to you. So wj of new equal to wj of previous plus alpha into dou by dou wj of jw. Okay. So now what you do is the previous, you got the dou by dou wj of jw. Now if you do this, so you will get that wj of new, the weight of new will be equal to the weight of old plus alpha, some alpha into 1 by m, where m is the total number of samples, into sigma of this yi minus wj xji into xji. This is for that particular this thing. All right. Now, that alpha is called the learning rate. So this can be controlled by you. This can be controlled by you. Okay. So this expression is correct. Your question may be right. I'll go back and check whether there is a typo, but there is nothing wrong with the formulation. This answer is correct. Okay. Who asked that question?
Sir, I had asked Soumya.
Okay. Okay. So I'll keep it in mind. But this form is correct now. Wj nu equal to W. So when we actually work out, so I hate this PPT because now if you're all here, I will just go to the blackboard and start talking. But since we are in an online world, even today, so I'm not able to get that on this thing. All right. I hope it is okay. Otherwise, when I actually derive, we can find out where the mistakes are. In a PPT, it's very difficult to find. Okay, because I'll get stuck, right, when I proceed. Let's see. So Wj of new equal to Wj of previous plus alpha into 1 by m, sigma I equal to 1 to m, y of I minus Wj xji into xj of I. Soumya, one way of checking it would be just to take the linear estimator problem, right? And then check whether this formula, so whatever equations we derived, right, for just see whether the same equations you get when you apply this. Otherwise, there is a problem with this slide, whatever has been. So there is a typo in this. All right. Okay, now, is that a convincing answer?
Yes, sir.
All right. Okay. Right. Okay. So because I wrote it in with hand and then it was scanned and it went to Chennai and Baki reached it, then I've checked it. So there could be some transmission errors. All right. So what we have essentially done is you start with a series of weights and then using this rule of an alpha, the previous plus alpha into that. So you keep on changing the weights. After you keep on changing the weights for each, at the end of each iteration, you'll get W1, W2, W3, all the way up to Wn. You also know X1, X2, X3. You'll be able to calculate the Y. Okay. And you'll be able to calculate the Y across all samples. Therefore, Y calculated minus Y data, you just square it. Sigma of all that. Okay. That will be your J. Of course, 1 by 2m, whatever. That is Chuma. That is just a constant. So just see whether it is going down. Okay. And then when the J goes down to 1e the minus 6 or 1e minus the 4, you just stop it. Okay. So if it misbehaves, it goes up, then you fine tune the value of alpha and proceed and so on. So this is the basic gradient descent, which we have explained it for a linear operator. All right. So here alpha is the learning rate with the value between 0 and 1, which controls how large a step we take during each iteration. So if alpha is large, we are taking a huge step because this orthogonal direction. So this direction, this orthogonal direction, gives you only the direction. In this direction, how much you go, okay? This is decided by alpha, you understand? Okay, for example, if there is a function like this or something, right? So this is x1, this is x2. Okay, it's a two variable function. So this is your y1, y2, y3, and so on. So this is your y minimum. This is where we are. This is where we are heading. Suppose you start like this. Okay, you start like this, and then you say that this orthogonal direction is like this. So the orthogonal direction is here. So from here, your next step will you take here or here or here or here. That is your alpha. Okay, or in the current step, you can also iterate for, you can also solve it for alpha and proceed to the next step. So that is also there. That I will teach you a little later. So finally, so for example, so maybe it's actually, suppose it is like this, you may go like this. Okay, and finally reach here. So these are the various iterations possible. So this is just a depiction of a minimum of this gradient descent, or a gradient. In this case, the gradient ascent, or I don't know whether it's gradient. So it's still gradient descent. So why is it called gradient descent or gradient ascent? If you want to approach a maximum of a function, you do hill climbing. So it is a gradient ascent. If you're approaching the valley, the bottommost point, it's a gradient descent. It's just a semantics. All right. The key advantage of the gradient descent is that it can be applied to any function for which the direct solution is formidable or not practical to obtain. Okay. Now this example will make it clear. Soumya, this example will make it clear. Now find the optimal weights which minimize the cost function. Okay. I think if you, instead of watching the lecture like watching a cricket match or a tennis match, Nadal is playing Djokovic or something, if you can take down your paper and pencil and please try to co-work with me. In that case, the alpha will be very high. The alpha, which is the learning rate of the class, will be very high. All right. Okay. So I'm switching to Blackboard, so that will slow me down. So let it be. No worries. What is the function? I can't see the. Please tell me. So J equal to 8 plus
W1 square by 2
Ah.
plus 2 by W1 W2
Ah.
plus 6 W2.
6W2. Okay, because I can't see the right one. It says Balaji is talking and something it is showing the zoom. Okay. Now gradient descent. Alpha is 0.05. Okay, and W1, W2. So W is a vector. Okay, W is a vector of weights. Okay. W means it is qualified as W1, W2, W3. In this case, it is 1, 1. All right. So now we are trying to use the gradient descent. So we have to calculate this del of J. Okay, there's a partial of the J with respect to the weight. So it is dou J by dou W1, dou J by dou W2. Okay, dou J by dou W1 is 2W1 by 2 minus 2 by W1 W2 square. Okay, all right. I'm not looking at the slide now. Okay, whatever I'm writing is correct and the slide has to follow me. Dou J by dou W2 is minus 2 by W1 W2 square. W1 square W2, correct? So W1 W2 square plus 6W. Is it right? Now we just see how I'm switching to heat. So we are starting with something is written, no? Initial guess of the weights as 1, 1. Okay. Initial guess of the weights as 1, 1. So initial the weight vector. Okay. Zeroth iteration is basically 1, 1. Now we can calculate the J of 1, 1. J of 1, 1 is this. 8 plus half plus 2 plus 6. 16 and a half. Okay, correct. So this is 16 and a half. Now we can also calculate the del J. So del J of 1, 1 is 1 minus 2 minus 1. Then minus 6 minus 2 plus 4. Okay, 4. So far so good. Is everybody with me?
Yes, sir.
Oh, very good. Okay. Now, I don't know what to erase. Let us try now. Huh? Let me try to work with this. Okay. So far, so good. Okay. Now we write this equation. W1, W2 of 1 equal to W1, W2 of 0 minus alpha del J of 0. Is that correct? That is you can put minus alpha plus alpha, doesn't matter. Okay. So this is basically 1, 1 minus alpha into minus 1, 4. Now we just decided, we agreed that alpha is 0.05. I think so. 0.05. Therefore, W1, W2 of 1 equal to 1.05. 0.04, 0.2. 1.2 is it? Minus. Yeah. This is a minus into minus, so this is 0.8. Okay. So now you got new W1, W2. Now you calculate the J of 1. J of 1 is 8 plus 1.05 whole square by 2 plus 2 by 1.05 into 0.8. That's 6 into 0.8. I think Balaji has worked it out. It's about 15.7. So it's good. So from 7, so we made some progress. From 16.5, we came down to 15.73. Okay. So you can calculate del J of 1 and so on. So the error is 0.5895. The error between the first and second is 0.5895. Repeat the procedure till the error becomes less than 10 to the minus 6. Is this clear? So gradient descent, which can be applied to any nonlinear equation. So it can be used for curve fitting regression. So today I've taught you nonlinear regression, which can be applied even if you are not where I am from. I am now looking for the cap. Okay, so I taught you that will upset me because it will get dried up. All right, so I thought it will come, it will resurface after some time. Don't worry about that. So you learned a very powerful technique today without you realizing that. Then we can do a lot of improvements over this. One improvement over this I will teach again using the blackboard. So this is essentially the gradient descent example. Okay. So is everybody with me? You understood it? Now you can proceed. So iteration. Okay. Similarly, weights for calculator for all the consecutive iterations till convergence is reached. 1 into 10 to the power of minus 4, whatever. At the 10th iteration itself, it is reduced. So first iteration, 0th iteration, W1 is 1, W2 is 1, cost is 16.5. The gradient was minus 1, minus 4. Error, you don't calculate. Go to the next one, 1.05, 0.8, 15.73. We calculated. Then the next one I skipped. That 1.27 minus and 3.02. That is here. So you proceed until convergence is achieved. So you crack the problem. And then finally the weights are, you look at the end of the, so looks like, I think it is just 1.5 and half. It is the way it is going. It approached 1.48 and 0.47. And my hunch is it eventually reach W1 is maybe 1.5 and W2 is just simple half. Okay. Is this example clear enough?
Yes, sir. W2 is actually decreasing, sir. So it will be less than half. W2 is decreasing.
Oh, it is decreasing. Okay. Maybe it is 0.45. Yeah.
Yes, sir. Maybe.
I don't know. Maybe. So you can just do this example. You can Python it. You can R it. You can Fortran it. Whatever. Huh? So just like you're Swiggying it and Zomatoing it, you can do whatever you want. Let's make everything into a verb. So you just try this. So it will be just unalloyed fun. Okay. So let's go to the next one. So you learned a very good algorithm today. All right. So be happy. All right. Can we do better? Now the question comes, can we do better? Sir, what is this 0.05? This 0.05, whether will it make life miserable for me? Huh? Whether will it make life miserable? Whether it will converge? Can I accelerate the convergence? Yes, of course. There are smarter ways of solving the problem. There's a host of algorithms developed. So this is welcome to the subject of optimization. This is basically optimization. Okay, so I specialize in that also. So I've written a book. There is an NPTEL course by me on optimization. You can watch all the algorithms I teach there. Okay, so this is a wonderful world of optimization. Okay, where you learn a lot of techniques. I got that. I got that cap. Now, so I'm at peace with myself. All right. Now, Cauchy's method. What is this Cauchy's method? The Cauchy's method says that this alpha 0.05 seems to be an external fit. Okay, what happens if it is a misfit? Okay, so there should be some more scientific way of solving this problem. So maybe if alpha is chosen to be very small, the convergence could be very sluggish. Therefore, suppose we take some adaptive learning near the optimum, the method can converge faster also. So needless to say, because of the name steepest ascent or steepest descent, we know that we are going to use the information on the derivatives in order to develop the algorithm. So we'll go in the direction of steepest descent. So this is due to Cauchy. So the steepest descent or ascent algorithm is the Cauchy's method. In that case, what we do is we use gradient descent, but alpha is calculated at every iteration. Okay. So same thing like previous, Wj new equal to Wj. So this doesn't change. Okay. So this doesn't change. Wj new plus alpha into J of W. Okay. The funda is alpha. The alpha is not fixed asset. Okay, the gradient, the direction in which the function changes is very fine. Okay, so let's say from here I want to go to which place? Southwest of Bangalore somewhere. I know that the general direction is southwest, but we are not crow or a bird, or we cannot fly as there is traffic and there are only certain routes available. So though you're fixing the direction, you say in that direction how much you will go. Okay, you go to Malleshwaram and then you take a left or a right, and then again you'll take a right, and then this white topping is going on somewhere, it is one way. So like that you'll have to correct. So we don't have wings, we cannot just fly to the other place. Okay, so when you're doing a steepest descent, how much will you go in that direction? So basically it leads to another interesting optimization problem. So at each and every iteration, we can minimize the cost function with respect to the learning rate alpha. Hence, the problem turns out to be a one variable optimization problem in alpha in every iteration. Okay, now do that. Let's go to the same example. Now, the class is with me, I hope so. So 8 plus W1 square plus 2 by W1, W2, 6W2 using Cauchy's method. Now, calculate the gradient, 0th iteration. Now, calculate W1, W2 of 0, which I mean, that is initial guess. J of 11 is 16.5. We just calculated. The del of J of 11 is minus 1.4. Now, what we do now is we choose alpha in such a way that 1 minus alpha plus 1 plus 4 alpha is minimized at, okay, J of 1 minus alpha and 1 plus 4 alpha is minimized. You get it? Okay. Oh, sorry. Okay, now we already got this. we already got this -1 and 4. Now what we are going to do now is, we choose alpha such that j of 1 minus alpha and 1 plus 4 alpha is minimized. Okay, that is eight plus now y is like this. Now I converted it to a single variable optimization problem in y. Now I can do in alpha. So now I will put dy by d alpha equal to 0 and get alpha. Is that clear to you? Is that clear to you? Okay. So once you do that, it doesn't mean that we have got the solution to the problem. We are moving in the best possible direction and the length for this particular iteration. Now, if you do this, now you can see 1, 1, same dou j by w1, dou j by w2 is the same, but alpha is now minus 0.12. Now, with that alpha, calculate delta w1, delta w2, go to the next iteration. Each time calculate the alpha, and you can see in the 6th iteration, it is 1.674 and 0.446. Soumya, whoever said that 0.45 is correct and 1.65. So I stand corrected. I said 0.5. These solutions are believable, right?
Yes, sir. Looks like.
Okay, looks like. Now let us do one very simple problem. So you see now you see the power of the blackboard. Forget the power of the PowerPoint. You see the power of the blackboard. Let me work out the Cauchy's method with a very simple example, but the point will be conveyed more effectively. Cauchy's method. Minimize. Array, what is this problem? Are you able to see the solution? What is the solution? Can you see the solution? What will be the solution to this problem? Can someone respond? Oh, then I will sing the national anthem. Am I audible? Am I audible?
Yes, sir.
So you're not able to see the solution. Okay, let's see.
8 and 6.
Okay, let's see this. 2, 4, 6, 8, 10, 12. X1. X2. 0, 0. This fellow is 0, 0. Leave him there. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10. 2, 4. Okay. Now this is basically the equation of a circle. Okay. X1 minus a whole square plus x2 minus a whole square b whole square equal to r square, where r is the radius, right? So some old geometry you're able to recall. So now basically you can draw various concentric circles around this. What are these? Each of these concentric circles has a y1, y2, y3, y4. The minimum, so the minimum will be a circle with 0 radius with a center equal to 8 and 6. Therefore, it is intuitively apparent. It is so intuitive, so you're able to intuit that the solution has to be x1 plus or x1 optimum is 8, x2 plus equal to 6, and y plus equal to x1 minus 8 whole square plus x2 minus 6 whole square. Y plus is nothing but 0 whole square plus 0 whole square equal to 0. Anyway, it is a sum of two squares. It cannot become lower than 0. And you got 0. So be happy, celebrate, buy a cake and eat it. So this solution is fine. Now you're able to see this?
Yes,
Huh?
sir.
Now we use a Hyphanda method. That is our Cauchy, our great friend, huh? Cauchy. Let us apply Cauchy's. So it may be like taking a AK-47 for killing a mosquito. Doesn't matter. But we want to learn the method properly, right? So let us solve it using the Cauchy's method. So please keep this solution. This is the y. We want to solve it. Now there is no common sense. Okay, we feign. We pretend that we don't have common sense. Sometimes we don't have to pretend. Actually, we don't have sometimes. Okay. All right. Doesn't matter. All right. So we want a maths guided solution to this problem, which is so apparent to intuition. All right. So I don't know where the solution starts and whatever. So let us start with an initial guess. Please recall that it is nothing but your previous problem also, right? It is like this. W1 to W2 is your vector. So it is like this. Okay. You put it in bracket. Okay. So dou y by dou x1. That is nothing but dou j by dou w1. Okay, equal to 2x1 minus 8. Dou y by dou x2 or dou j by dou w2 is nothing but 2 into x2 minus 6. Now we also said that this fellow is at 2, 2. Now at 2, 2. Minus 12. 12. I think I'm doing fine. Dou y by minus 8. Am I doing okay?
Yes, sir.
Now, Cauchy. Now, y of initial guess W1 plus alpha W2 plus alpha now I will switch over from the, where is the tester? I will switch over from so that it is concordant with what we are solving. All right. So y of 2 plus 2 minus 12 alpha. 2 minus 8 alpha. So now I have to evaluate y at these 2 points. But y, what is y itself is this. That's good. All right. So now y equals 2 minus 2 alpha minus 8 whole square plus 2 minus 8 alpha minus 6 whole square. Y equals. Is it correct? Is this correct?
Yes, sir, it is correct.
It is correct. So 36 into, because it is 1 plus 2 alpha into 6, 6 into 6 are 36 into 1 plus 2 alpha. I can do that. Plus 16 into 1 plus 2 alpha whole square. So I think y is something like 52. So I'm on a slippery slope. So can somebody please point out if I'm wrong? If I'm proceeding the right direction, just listen. This is okay. So now you make dy by d alpha equal to 0, which means, okay, 2 into 1 plus 2 alpha into 2 equal to 0. Therefore, alpha equal to minus r. Is that okay? Now this is different from, please look at the PPT now. So this is different from this first very elementary, or determine the optimum weight alpha equal to 0.05. Okay. Now we have, if somebody's, I'm getting some background noise, please mute yourself. So this is quite different from this example where this alpha equal to 0.05 was assumed, and then it is constraining us. Now I'm trying to, but I'm doing more work. I'm doing more work, but I'm able to get this alpha. Now with alpha equal to this thing, so x1 new plus okay. Now what is it? Minus half. What? Super magic. How did we get it in one shot? Array, the function is quadratic. Therefore, when you take this, when you use the Cauchy's method, the j's are all linear in the weights, in the x1 and x2. So therefore, it will one shot you'll get it. Suppose you go to a cubic or a quartic, it will take struggle a little more. But now, class, please tell me. So Cauchy's method, find optimal weights. I put this PowerPoint. Now I solved one more problem on the blackboard, which got the point across in a better way. Oh, somebody should respond. Huh? Hello?
Sir, can you repeat the question, please?
No. One example I just showed in the slides. One example I showed on blackboard. It is the same message I conveyed. Which conveyed it better?
Of course, the blackboard one, sir.
That is why. That is why. Blackboard is supreme. All right. So you got it. So now there are some advanced algorithms. So instead of going, so what you can do is you can get alpha 1, alpha 2. Okay. So if alpha 1 and alpha 2 are like this, then you can, so if it is alpha 1 and alpha 2, you can go in new direction called alpha 3, which is called a deflected steepest. So that is called the conjugate gradient method. Okay, so you can apply it for a multivariable problem. So already we did it for a 2-variable problem. So you have learned in today's class, apart from data science in ML, so you have learned a powerful optimization technique for a n-variable problem without constraints. So with constraints, it's a little tedious. So you have to take a course. All right. So that's good. Now comes the logistic regression. I don't know what the time is. Let me check it. Oh, 5:25. Okay, so let's go to the next one, logistic regression. Logistic regression is the gateway to machine learning. Okay. Now, in linear regression, we saw that the outcome or the variable was numerical, as often it is. Now the question is, what happens when the outcome variable is not numerical? Example, crossing the road. The outcome is basically I either cross the road or I don't. I'll just drink water. I cross the road 1. I don't cross the road 0. But variables can have all sorts of values. How many kg of weight I'm carrying and all that. And what is the speed at which auto rickshaw is coming? What is the speed at which some Honda City car is coming? Whatever. But output is I either go or no go. All right. Let's take another example. Let us say a weather data set with the attributes humidity, temperature, and wind speed. Each is describing one aspect of the weather for a day. So we'd like to predict if it is suitable for playing outdoor games. If you feel that, sir, it is all anachronistic example, you say, you feel whether, I don't know what is a cool place to hang out for you guys. Whether you want to go to Brigade Road or you want to go to a mall, or depending on the weather, you will take a call on this. Suppose humidity, temperature, and wind speed. Based on this, you'll take a decision. You'll either play sport or go to a mall or what have you stuff. In such cases, the outcome that we want to predict is S, 1 or no, 0. So the regression problem now, the same regression problem, but the output is now 0 or 1. You understand? So far, the output is basically what is the square of the radius of the circle in this case, or in that y objective function and all that, which can be real numbers. Now the objective function is a 0 or 1. So the regression problem now turns out to be a classification problem. If it's a linear combination of masala of all the weights and your attributes, the output should always be a 0 and 1. So can you model it and tell me, if I tell you the humidity, temperature, and wind speed, can you tell whether Pradeep will go out of the campus or not? Okay. So if you're able to do that, you're doing logistic regression. You're just one step closer to ML, machine learning. All right. It is a classification problem. What is this classification? Classification into 0 and 1. Okay. Unlike linear regression, here we have only 2 possible values, labels for the outcome, 0 or 1. Okay. While we have continuous values, please note, while we have continuous values for the input, we can have only 2 possible values for the output. For example, rainfall is dependent on many factors. But suppose I want to classify the rain as convective rain or stratiform rain. If I say stratiform is 1 and convective is 0, so whenever I put 1, it is stratiform in a pixel, and 0, it is convective. So I put the whole pixel in terms of zeros and ones. Okay. That if it is an outcome of a model, and I may be doing so much of calculations or some theorizing or hypothesis to translate my variables into convective or stratiform. But finally, is it convective or stratiform? Okay. Are you crossing the road or you're not crossing the road? Will you go to the mall or you will not go to the mall? Will you study for the exam or you won't study for the whatever? Suppose there is a binary, this thing like this. So how do we do all that? There is a magic function called sigmoid or logistic function. It has got this magic function. Now f of x is 1 by 1 plus e to the power of minus x. Okay. So it is also called like that. So also called a learning curve. We say no, it has got a steep learning curve. That is a steep learning curve. So initially the output will be very less for a long time. Then suddenly there will be non-linear increase. And then, so this is phase 1, phase 2. This is like your PhD. First 2-3 years, you don't know what is happening. You feel you're liberated, you're getting scholarship. You can Amazon what you want, you can Flipkart whatever you want, you can buy fancy mobile and Fitbit watch, whatever. But time will be running out. Okay, because 3 times you're getting food, you're in the hostel, so somebody takes care of everything. Life is so easy. But now time is going, there's no output. Okay. Then pressure comes, right? Because your friend got a paper. Okay, he got in a high impact journal, and then that puts pressure. Okay, so and you're also looking at this thing already 3 years are over, and so the learning curve is this. Then suddenly your code is working or your experiment is working, so there is a non-linear progress. Once it crosses 7, 8, 9 years, again even the progress it is asymptotically it will saturate. So any learning will be like that. Initially we struggle, then there'll be explosive learning. Then if you keep on spending a lot of time, there is no additional there's an incremental learning. So the same thing is there. So f of x is 1 by 1 plus e to the minus x. So this is our hypothesis function, the proposal function, or you call it a g of z. Z is a dummy variable, 1 plus 1 by 1 plus e to the power of minus z. This outputs continuous values between 0 and 1. What is the beauty of this? What is the beauty of all things under the sun, over the sun, above the sun, everything can be captured. What do I mean by that? If x equal to minus infinity, so this has a function, this has 1, correct? Oh, sorry. If x equal to minus infinity, this is 0, correct? Is it correct?
Yes, sir.
Hello?
Yes, sir. Correct.
When x is plus infinity, it becomes 1. Therefore, all the variables, when they vary between minus infinity to plus infinity, this magic function has got only an output which varies between 0 and 1. There is no function which can come close to it, because you can capture all the variabilities, all the nonsense in the world. It can pick it up and then convert it into something between 0 and 1, which is positive. The lowest is 0, the highest is 1. So this is a godsend. How will man not use it? Of course, he uses it. So this is the gateway to machine learning. So you will put all the masala and then you calculate the probability. Probability will be 1 by 1 plus e to the power of minus z. If the probability is greater than 0.5, you say that I will go to the mall. If it is less than 0.5, you don't go to the mall. So that probability can be 0.5, 0.6, 0.7, whatever, but it will be mutually exclusive. For example, if the probability of going to the mall is 0.7, automatically the probability of not going to the mall will be 1 minus 0.7. Okay, so if P is the success and Q is the failure, P plus Q equal to 1. Okay, and all the nonsense in the X can be from minus infinity to plus infinity. This returns a value between 0 and 1. So this is very beautiful. Okay, so this probability finally we convert into a digital output of 0 and 1. So this Z is basically what is riding on the Z? The Z is basically the hypothesis function. In that hypothesis function, I can put all my weights and all my variables. You can put whatever you want. My mood. So I want to go to the mall means your mood. How much balance you have in this thing. Whether you had a good meeting with your guide. Okay. Then your health is fine. Whether the weather is fine. So you put it as X1, X2, X3. You W0, W1, W2. You'll have to figure out. Okay. But the W0, W2 you already figured out in your brain is. So that's why you take a decision. Or your friend calls, hey, come, let's go to this Orion Mall. So, no, I'm not coming. How do you take the decision? So you are processing that. You are doing a sigma inside your mind because it is progress. So there are plenty of gray matter there. He's doing it all the time. But now in this machine learning, we're trying to say how we are doing it naturally, and then can we put it into engineering systems or scientific systems so that we can understand, we can predict, we can do analytics. That is the whole idea. Now the Z can be W0 plus W1, X1, W2, X2, so on up to Wn, Xn. W's are the weights, just like the weights we found out now. X1, X2, X3 are the features, or the attributes, or the variables of the problem. So since the hypothesis function always outputs between 0 and 1, one can draw a threshold of 0.5 and say that if the outcome is greater than 0.5, then we put it in class 1. That is, the weather is suitable for outdoor games. The weather is suitable for going to a mall, or weather is suitable for doing something. I want to run in the gymkhana at 8 a.m. or 7:30 a.m. provided I wake up. Okay, for which you'll have to sleep at least at 1 a.m. Okay, if you sleep at 3:30 a.m., like most hostelers do, how will you run in the gymkhana at 7 AM. That's not possible. So then the probability is given by P of y equal to 1 given a set of, please now say it's a conditional probability. The probability of y equal to 1 given x dot w is hw of x. Otherwise, it goes into class 0. The probability will be 1 minus hw of x. The total probability will be the probability of success into the probability of failure. The probability of any y given a set of x and the weights w equal to the probability of success multiplied by the probability of failure. Okay. So we can check for its asymptotic correctness. When y is equal to 1, watch my, now when y equal to 1, go to the red one. The second term becomes 1. So when y equal to 1, P of y of xw is hw of x. This is basically the first bullet. Go to the top of the slide. So when y equal to 1, the probability is hw of x. It is success. When y equal to 0, the first term becomes 1. The second term stays there. Second term becomes 1 minus hw of x. So therefore, asymptotically for both the limits, it is correct. Okay. So who is the genius who found out this? The total probability in success and failure can be modeled as h of something to the power of y into 1 minus h of something to the power of 1 minus y. It is our friend Bernoulli. Okay. So I will do the Bernoulli for another 5-10 minutes and close the class. So the logistic is too deep, and I'll also give an example in atmospheric science. Okay. So I'm sorry that I miserably miscalculated. 1 hour, we have just finished gradient descent, just introduced this thing. That's okay. But I think you're able to follow what I'm saying, right? The speed is right, isn't it?
Yes, sir.
Okay. Anyway, we'll take 1 more week, no problem. All right. What is a Bernoulli experiment? A Bernoulli experiment is a random experiment, the outcome of which may be classified in but one of the 2 mutually exclusive events, say success or failure. Example, heads or tail, female or male, life or death, rain or no rain, convective or stratiform rain, etc. Okay. A sequence of Bernoulli trials occurs when a Bernoulli experiment is performed several independent times, so that the probability of success remains the same from trial to trial. Okay. If the probability of success is P, failure is Q. All right. Therefore, Q equal to 1 minus P. Both are proper. Okay. So this means that Q and 1 minus P can be used interchangeably. Is everybody with me? Is it okay? So Bernoulli trial is like the tossing of coin, heads and tail. Okay. Now, let x be a random variable associated with the Bernoulli trial by defining it as follows. X equal to success equal to 1 and x of failure equal to 0. I come again, x of success equal to 1, x of failure equal to 0. That is the outcome success and failure denoted by 1 and 0. The probability distribution of x, also called the probability mean function, f of x, can be written as. So this is the beauty of the Bernoulli. F of x is written as p to the power of x, 1 minus p to the power of 1 minus x. Okay. So this is nothing but q. All right. So x is 0, 1. We solve the problem. Now it looks threatening, but it's not so. It's very nice. This is a Bernoulli distribution. They expected, what is the mean value? What is the mean value? Okay. Mu of x equal to sigma of x equal to 0 to 1 x of. So I have already told you, right? So x of f of x, right? X equal to 0 to 1. Okay. So in this case, there are only 2 values. So that f of x is basically your p of x into 1 minus p of 1 minus x. So let us expand it to only 2 terms. First term will be x equal to 0, p of 0 into 1 minus p into 1 minus 0. So the first term is 0. Second term will become 1 minus p of 1 minus 1 is 0. Second term will become p. Mu equal to p. Now it looks what is all this so intricate? Nothing. If there is a fair coin, the probability of success is 0.5. The expected value is 0.5. The expected value of x is 0.5. If it is a biased coin, then it will show you what will be the expectation. If you put some like the Sholay movie or something, if you put something on the heads, you put some Fevicol or something, then you bias the coin. Then if it is 0.8, then the expected value will be 0.8. What is the expected value? 100 times you toss the coin, the average will be, 80 times, 80% of the time it will return that P. If it is an unbiased coin, it will be 50 times. If it is a biased coin where you did some golmaal on the head side, then you'll get it as 80.8. Is that okay? Now we can do the variance. Variance is the x minus p whole square into the probability. Expand it slowly. In the interest of time, we'll skip it. So sigma square is pq, but I know that q is 1 minus p. Therefore, the standard deviation is root of pq. Therefore, this Bernoulli distribution is very, very important for us because our logistic regression will ride on the Bernoulli. So I'm beginning to use technical terms now. Okay. So the gateway, so it is basically a logistic regression. Writing on a Bernoulli. With a linear estimator. See, so much, it is so nuanced. It is so nuanced. Okay. With a linear, what is a linear estimator? I will go to the gymkhana or I won't go to the gymkhana for running. So W0, W0 the weights. X1 is what time I slept. X2, whether my health is good, what I had for dinner, blah, 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 all that. So, all right. So you have got a linear estimator for that Y. Okay. Then it is riding on a Bernoulli distribution. Okay. Because you're doing the repeated number of trials. Then you're doing a logistic regression because the outcome will be 0 or 1. You have to use a logistic regression in the end. So therefore, there are three things here. There is an estimation problem or a regression here. There is a Bernoulli distribution. There is a logistic regression. So the combining of this, finally, a set of inputs is finally you decide success or failure 0 and 1. So it's a classification problem. So you start with attributes and then you classify. This is exactly the same way in which the brain will process when multiple signals are coming and you have to take a decision. Okay, whether you will go for this interview or you will not go for this interview. You will take these 4 courses, you will not take this. Okay, whatever. All right. Now, all right, this is done. Variance is done. So in a sequence of n trials, let xi denote the random variable associated with the ith trial. An observed sequence of n Bernoulli trials will be an n tuples of zeros and ones, as we frequently call this a random sample of size n from a Bernoulli distribution. So, okay, now all this is very theoretical. Let us say that we plant 5 seeds of a particular plant, and we want to see whether the seed grows germinates into a plant. Let the probability of germination of seed be 0.8, and 0.8 we call it a success. If the germination of one seed is independent of the germination of another seed, and we plant 5 seeds, what will be the probability of occurrence of the sequence 10101, where the seeds 1, 3, 5 germinated, while 2 and 4 did not? Is the question clear to you? Just read the question. I'll close in 5 minutes. Is the question clear?
Yes, sir.
All right. Now, total probability is, first is success, P. Second is failure, P into 1 minus P into P into 1 minus P into P. Because I have to get all these things. I have to get this sequence. Therefore, the joint probability is a product of the probabilities. Is that clear? And the first one is successful, P. Second one is failure, 1 minus P. Third one is success, P. Fourth one is failure, 1 minus P. Fifth one is success, P. So if I write that, P into 1 minus P into P into 1 minus P into P. Now P is given to be 0.8. How? I told you success of probability of germination is 0.8. Okay. Then if you do all that, finally to get that sequence is 0.02048. It is quite small. You got a 1 in 50 chance. You have a 1 in 50 chance of getting it. Who is the great guy who figured it out? This is Jacob Bernoulli, 1655 to 1705. Incidentally, he also discovered that limit n tending to infinity 1 plus 1 by n to the power of n equal to E. Okay, that E which troubles you so much in life is thanks to Bernoulli. Okay, so I think already it has become heavy now. We will stop here. All right. Okay, any questions so far? Is it okay? So just do a thumbs up if you're able to, if you followed the material in today's class. All right. Okay. Thank you very much. So I think logistic regression has to wait for. Thank you very much. Thank you, Tejal, Soumya, Pradeep, Ankit, Shobik. All right. Thank you. And some names whom I might have missed. Krishna Kumar. All right. So see you. It's time for coffee now. Okay. So there is no 0, 1, whatever we have to have. I need to have at least. Chalo. Bye.
Bye, sir. Thank you.
Bye. Bye.